We want to numerically integrate some functions in R. Integrate is a built-in R function which performs numerical integration, just what we want. The format of integrate is integrate, the function name, the lower limit of integration, and the upper limit of integration. You can also use the word lower equals the lower limit, upper is the upper limit as part of your arguments. F itself must be an R function with a numeric first argument and a numeric result. Let's try some examples. First of all, what if we wanted to integrate a built-in R function? For instance, sine of x. Really simple. Integrate, name of the function, lower limit, upper limit. We're using the constant pi, which is R's representation of pi. By the way, note the lack of arguments in the function. Just the function name is used here. The answer is 1. Something called absolute error is 1.1 e to the minus 14th. That's basically 10 to the negative 14th power. Pretty accurate. If we actually wanted to use this for something, it's probably best to assign it. So in this case, I'm assigning the result of the integrate command to a variable called zt. Notice I have my parentheses, so it's going to do the computation and still says 1 with absolute error 1.1 e to the minus 14th. But now we have a little problem. What happens if I try to add 1 to the value of zt, which looks like it's 1? Lo and behold, I get error. It says non-numeric argument to binary operator. What's the problem? Well, the result of integrate is not a number. It's actually what is called a list in R. I'm going to use this structure command to actually list the list. And lo and behold, this says it's 5 different components. The first one is value, a $ value. The second, the $ absolute error, etc. The one we're usually interested in is the value component. If I just take the value zt $ value, I get 1. Notice the error less than 1.1 e to the minus 14th is not there anymore. And I can also do arithmetic with this. So basically, I took the component I was interested in and can now work with it. Though it's a little long to name a variable zt $ value, so we could just do an assignment with this. So notice ZTT is now defined as ZT $ value, and ZTT plus 1, 1 plus 1 is 2. Programmers often work the following way. We're defining ZT $ value as the variable ZT. Now we already have ZT from the integrate command. What this does is it redefines ZT as the ZT $ value. The old ZT is gone. So ZT is now a value if I work this way. Programmers use this a lot. Now, I don't have to only use built-in functions. I can actually use a user-defined function. So here's a function I'm defining, x cubed plus x squared minus log of x. Let me show what that looks like between 1 and 4. Here it is. And notice it's a pretty simple function. I actually want to find the area under this curve. That's what the integrate command actually does. Finds areas. How do I do it? Pretty easy. Since I've defined f already, I could just integrate f Notice no arguments. Lower equals 1, upper equals 4. And I get something like 82.20482. And here's the absolute error. If I want to do arithmetic with this, I'd assign it to a variable and take the $ value component. As a rule, if you're going to use the result of the integral later, assign it to some variable. If it's just going to be a value, it's really not necessary. Now, here's an interesting way that you can use integrate. Essentially, we're virtually defining a function within the integrate command. We're not giving the function a name. Here it is, ZTZ, it's integrate. And notice within the integrate command, the first argument is function x, brace, 1/9 times x squared, end brace, lower equals 0, upper equals 3. Got the one I wanted. And I still have a list. So if I define this, ZTZ is now a variable, has the value 1, and it's ready to use in arithmetic. Okay, so next example shows you that this virtual definition is actually kind of useful. In this particular case, I'm defining T as actually the density function of the uniform. Remember, dunif is the built-in density function for uniform random variable. Notice the boundaries in this case are 0 and 1. I want to find the expected value in the variance of the uniform random variable. Well, remember the definition of expected value. It's the integral of x times the density of x over the limit. It says -infinity to infinity, but basically this is 0 to 1 because it's the only place that it is defined as positive. And so the integrate command ends here. And the $ value says, hey, let's take the value all at once. And that's going to be EX. And notice we get a half, which actually makes sense. That's 0 plus 1 divided by 2. To find the variance, I'm going to find the expected value of x squared. I'm using my same TX that I defined over here. But now I'm going to change my virtual function. It's going to be x squared times TX. This is the expected value of x squared. And remember the variance? It's the expected value of x squared minus the expected value of x squared, which comes out to be 0.08333 in this case. Integrate even lets me use infinite limits. The key is infinity is capital I and F, and negative infinity would be negative capital I and F. This is integrating from 1 to infinity, and you got 0.5. Notice it converged. It's actually kind of neat. Negative infinity to -3, this is the area. The one problem that you might have is if you try to integrate a function that doesn't converge, the area under 1 over x between 1 and infinity is actually infinite, you get an error in the integrate command. And this is how you can use the integrate command to numerically integrate functions in R.